So I wanted to present Professor Tepedino because we need phenomenology, and he's professor in dentistry in L'Aquila University. And I think that he will give us an insight of what people trying to solve practical problems are experiencing, and this is very good for us. By the way, I want to tell you that he is so persuaded that he needs our help that he contacted me. Okay, so I will write this in my CV because he believes that theoretical knowledge, mathematical modeling is important in what is done. So let us hope that this is a long collaboration. Please.
Thank you. Thank you so much, Professor Dell'Isola, and thanks to the organizing committee for inviting me here. And I thought that it was mandatory for me to do that. I am a dentist, but Professor Dell'Isola told you this already. And so basically you will see the perspective of a clinician. So please forgive me if I will say something trivial or obvious about finite element model analysis. As I said, I'm an orthodontist. So basically what we do is try to correct a dental or a skeletal malocclusion. It could be either that we have a dental problem, so we move teeth in order to achieve a correct occlusion that is both functional and also aesthetics. And it also could be that maybe we have skeletal problems, and so we have to apply orthopedic forces in order to modify growth to reach a more harmonic situation. And we can do this with different techniques. We can use removable appliances, fixed appliances. For example, this one is used to apply a force to the mid-palatal suture and so expand the palate. Or maybe fixed appliances like this one. Or nowadays, clear aligners have become mainstream. So there is a lot of research ongoing on them. In any case, the concept is that we know that a prolonged pressure applied to the tooth will result in its movement. And so this allows us to move the teeth in the desired position. Orthodontic tooth movement is thus determined by a load adaptive response of all the surrounding structure. And the tooth is connected to the bone through a very special kind of joint. So we have a lot of fibers here that forms the periodontal ligament that acts like a cushion to absorb the very high load that we have during the mastication. And also, orthodontic tooth movement is a very nice setup to study bone remodeling in general. And I can say that there is a lot of research to do this, with this, because the funny part of the story is that we are moving teeth from more than a century, but we still don't know the exact mechanism that is going on when we use this kind of appliances. Many theories have been developed during the years. The first one was the pressure tension theory by Schwarz. And this is simply describing what we see clinically. Because I know that if I apply a force, an horizontal force to an incisor in this direction, what I will see over the months is that the tooth is moving in this direction. So in a way, there should be bone resorption ongoing here and here, and new bone formation here and here. So this theory says that here I have a compression because the force is moving the teeth inside the alveolar socket in this direction. and bone apposition where I have tension. Then this theory was further developed by Bomrind, who say that maybe it's not the compression or the tension of the PDL, but rather the bending of the alveolar bone under the load of the orthodontic forces. But all these theories have been questioned over the years because they contradict everything that we know about bone biology, okay? Because we know that compression means bone gain and lack of load means bone loss. But this is in contrast what we see, okay? And the reason for this discrepancy is due to the presence of the periodontal ligament that changes completely the way the load is transferred to the bone. As I say, the PDL is made of connective tissues, mostly collagen fibers, and fluid. And there are other strange things because we know that we need a certain threshold of strain to trigger bone remodeling, but all the forces that we use in orthodontics are far below this threshold. And also we know from the landmark study of Lanyon and Rubin that we need dynamic strains to trigger bone response, but typically orthodontic forces are constant and static forces. Probably it is possible to answer to this discrepancy through the concept of tensegrity. That is the tension balance that exists between the cells and their surrounding structures. And so probably it is the change in this static tension integrity that alters maybe the cytoskeleton, resulting in a cellular response that leads to bone remodeling and everything that we see. So in the end, it is possible that orthodontic tooth movement is initiated by a strain relaxation signaling. And this is able to combine what we know, what have been studied for long bones, for example, and what we see clinically for teeth. If we imagine the strain relaxation pathway, we can now understand that if we apply a force to a tooth, and what happens immediately is that the tooth moves inside the alveolar socket, we will have that these fibers will be stretched, and so the bone will be loaded here, and in the opposite direction the fibers will collapse, and so the bone will be unloaded. And this was finite element provided a lot of useful knowledge to reach this understanding. In fact, finite element is really useful for us because this kind of movement are really difficult to study in vivo. And clinically, we can have some simple situation where maybe we have a force system that is simple to study. For example, in this case, we have only a 3-point contact force system, so we can know that by applying a single force here of a certain amount, we will have another force here and also a rotation on this tooth. And what we see happening, we can calculate pretty easily this. But on the other hand, when we go to much complex systems, it becomes really difficult to know exactly what is going on because the system is too much complex. Don't be scared, it's not that we don't know what we are doing, but the problem is that we are dealing with forces, and for us, it is really important to know the amount of force that we are using, because there is a certain threshold, and if we go over this threshold, we know that we are starting to have tissue damage. So for us, it is really important to apply forces below this biological threshold. But when the system complexity goes up, it is almost impossible to know exactly the amount of force that we are using everywhere in the appliance. And so this could be a problem because we could have root resorption, for example. That is one of the undesired effects of orthodontic two movement that should be avoided. And this could be avoided knowing the force system that we are and how the bone is and all the alveolar structures are responding to the system that we are using. If we look at the current literature, there are a lot of studies where finite elements are used for orthodontic applications. I won't go through this because you can teach me how to explain all these things, but I simply want to underline that the interface between the root, the PDL, and the alveolar socket is really complex. And so if we want to have a model that is anatomically correct, we need to depict this complexity. We know that the periodontal ligament in normal condition is very thin, and that the interface between the bone and the ligament is very complex. It's not a regular surface, it's very uneven, and so this translates into the observation that macroscopic strains can result in very high microscopic strains, because we can have very small contact area where we can have very high strains. And another important aspect is, of course, the properties that are assigned to the materials. And concerning the properties of the periodontal ligament, there is a lot of research to do, because if we look at a recent review of the literature, there is a very large discrepancy in the definition of the properties of the PDL in the studies that are already present. And this results even 6 orders of magnitude of differences in the results that we are having. And this is because the periodontal ligament is a tissue that is really difficult to characterize, because again, it is really difficult to study in vivo which are the strains. So we need in vitro models or maybe mathematical models to try to understand the complex hyperelastic, viscoelastic, and anisotropic responses of the periodontal ligament. Recently, in 2016, it was proposed an exponential hyperelastic model that was also validated in vitro. This seems to reflect better than the models that were used before the real properties of the periodontal ligament. So, as we were saying at the beginning, there is a lot of research to do. And so I will, at this point, show you which are our main research lines in orthodontics. Nowadays, we are studying a lot clear aligners. Every year, the number of patients that are treated with this kind of appliances is increasing, because there is a great demand from adult patients that wants to have a nice smile with an appliance that is not visible and it is more comfortable. But there is a lot of research to do on this, because there is a lot to study about the material properties and also the biomechanical systems that are produced by this kind of appliances. They are quite difficult to study because compared to a metallic arch wire and a bracket where the geometry is very simple, the interaction between the aligner and the crown of the tooth is very complex. And it is constantly changing because we have multiple point of contacts, a complex geometry, so it is really, really complex to study the mechanics. And so the load that the root is experiencing while using this kind of aligners, the reason why they have not yet overcome the use of metallic brackets is that they are not yet as efficient as metallic appliances in producing dental movement. But this is only because a lack of knowledge on how the system is really working. And so, again, finite elements can provide a better insight in what, in the way this system is working and how the forces applied are experienced by the PDL. But as I say, it's not that we forgot fixed appliances. We, at the University of L'Aquila, we developed this system and we studied a lot how this system is working. This is used to have an impacted tooth, that is a tooth that is stuck inside the bone, and to have it erupted inside the mouth. Now we are currently studying on what is happening on what we call the reaction unit. Because of course we want this teeth to erupt, but ideally we don't want those other two teeth where the appliance anchored. We don't want those teeth to move. So it is interesting to know how the other units are experiencing the forces used by the appliance. And also, as I said at the beginning, we can have more complex systems where multiple forces, multiple loads are applied. And also here, there is a lot of research to do. Just to give you an idea, all the teeth have a slight forward inclination. Okay, that's the ideal situation. So when we first apply a wire that is so applying a force system to all the teeth, what we see is that all the teeth are moving slightly forward. In many cases, we don't want this to happen. So what many clinicians do is to apply such figure-8 ligature to these teeth in order to try to control the position of the front teeth. And some clinicians say that this is effective. Others say that what you will get is only that the posterior teeth will move forward more. And this is something that is really difficult to study in vivo because there are a lot of variables to be considered. So it is not easy to isolate one problem and study that. And in this kind of application, finite elements could provide very nice and very interesting data that will result in better treatment for the patients, better results, and more efficient mechanics. So this is the end of my presentation. I hope that I raised some interest in orthodontic tooth movement, and that this could be maybe a nice beginning for an interesting collaboration. Thank you.